Hi everybody, welcome to Compass Friday. Today we have Brian Soden, who's a professor of atmospheric sciences. This is part of our special Compass faculty seminar series. Brian specializes in the use of satellite observations to test and improve computer simulations of Earth's climate. His areas of interest include understanding climate feedback processes, the atmospheric hydrological cycle, and the response of extreme weather events to global warming. Dr. Soden teaches courses on weather, climate, and climate change. He advises professional master's students, doctoral students, postdocs, and research scientists. Brian was recently made a fellow of the AGU and is the current associate dean for graduate studies. So without further ado, Brian Soden.
Thank you for that very formal introduction, Eden. Okay, so these are kind of bipolar talks by nature. The first part, I'm going to kind of give an overview of the different research activities going on in my group, and then the second half will be more of a focused story about radiative feedbacks and tropical cyclones. Okay, so this is the research team. This is, Aiden, Chen-Young, Hauja, Sissom, and Eric. And there's a couple people that aren't here in this picture because one is Chen-Young, Mao Fang. He's a postdoc and he's remote, he's in DC. Mao Fang came here. He started literally the day after we closed for COVID. He showed up on Monday when UM closed, and the poor guy was isolated in a strange place in an apartment all by himself. I felt so bad. But now he's back in DC with his wife, working remotely and doing great stuff. And then Priyam is another postdoc. He's going to start in a couple months. He's also going to be working remotely. And then I'm also going to show some results from former group members, Bo and Shunan and Ryan Kramer. So those are the people. I just sit here and kind of try not to impede their progress too much. And I'll kind of give highlights of each person, what they're working on here. So Mao Fang, he's actually a civil engineer by training. He got his PhD in civil engineering at Princeton. And then he did some work on extratropical transition of tropical cyclones, and now he's on the ocean, so he's kind of very versatile in what he does. And he's looking at how ocean salinity affects climate. And one thing we know from model projections is that dry regions become drier, wet regions become wetter as the climate warms. And in the ocean, what that means is salty regions become saltier and fresh regions become fresher. So he's been looking at what the implications of that salinification of the ocean surface are. And one of the things he's found is that as you salinify the ocean surface, you actually reduce the stratification of the upper ocean. That leads to more heat uptake, especially in the subtropical regions, which aren't really thought of as key regions of ocean heat uptake. But it turns out, at least in model simulations, they're very important for that. And in fact, most of the intermodal spread, if you look at the IPCC coupled models, most of the spread between models and their prediction of ocean heat uptake efficiency is related to their climatology of subtropical salinity. So models that have a saltier subtropics in the mean state tend to have a greater heat uptake efficiency than models that have a less salty. And this process of heat uptake, also the salinification, reduces the transient warming. So the climate, Fang has a paper showing the climate now would be about 0.5 degree warmer if it wasn't for this salinification helping to sequester heat into the deeper ocean. And it also actually plays an important role in preventing the AMOC from shutting down. That's kind of his latest work. Next up we have Hauja. Hauja he just graduated, so he's now Dr. And he's going to be starting his postdoc. Well, actually, he's already started at Princeton, but he's still here, so he's kind of working remotely for a couple months. So, and he did a lot of different things, but my favorite thing from his PhD research is looking at radiative forcing from CO2. And this is something that we thought had been settled for almost a century. Our understanding of how CO2 traps heat and amplifies the greenhouse effect goes back to the 1950s. And we always thought it was constant. We always thought it was just a fixed value, like this gray line here. And what Hadja showed is that it's actually not a constant, that the rate of forcing from CO2 is actually a dynamic quantity that changes as the climate changes. And it opened just a whole new spectrum of research activities, the implications of that dynamic nature of CO2 radiative forcing. And I've just listed some of these here, sort of the areas that this work has implications for. And honestly, I think the sign of a good research paper is one that answers some questions but asks more questions. And I've never really been part of a paper that's kind of opened up more avenues for future research than the work that Hadja did on this. So it's really, it's just one of my favorite things to think about now. Next we have Sissom. Sissom is starting her 5th year now. She's looking at how the tropical circulation responds to a warming climate. And one thing that models have always projected is that the overturning circulation of the atmosphere should weaken as the climate warms. And Sissom actually just published, or just been accepted, the first paper that actually demonstrates from observations that we can actually see this weakening in the observational record. So using satellite measurements over the past 30 years or so, we can actually see about a 5 to 6% weakening of the overturning circulation of mass in the atmosphere. So, and that has, one of the interesting things about this is models tend to predict that weakening of the overturning circulation is manifest as a weakening of the Walker circulation. And in fact, what Sissom shows in the observations, the Walker circulation hasn't weakened over the past 30 years. So you can still get this weakening of the circulation occurring, it is occurring, even while the Walker cell is strengthening and the Hadley circulation really isn't changing. So that's other aspects of the zonal overturning, maybe related to monsoonal circulations, we're not really sure. So that's what Sissom's been working on. Eric is working on work that's kind of related to what I'm going to be talking about today. He's looking at how radiative feedbacks influence extratropical circulation, or extratropical cyclones. And honestly, I've never felt more useless in my life than trying to watch Eric understand the energy cycles of extratropical cyclones. I know absolutely nothing about it. I've been of absolutely no help in his work on this, and he's done really great work on it. I've learned quite a bit from it. And kind of, the thing that first attracted our attention is that I'll show, as you suppress feedbacks in a model, the frequency of tropical cyclones goes down, but the frequency of extratropical cyclones actually goes up. I said that the wrong way. Radiative feedbacks increase the frequency of tropical cyclones, but they actually decrease the frequency of extratropical cyclones. So there's this contrasting behavior between the two, and we think we understand it now thanks to the work that Eric's done, and it seems pretty straightforward that it's just the Planck radiative damping of the baroclinicity tends to decrease the baroclinicity. So when you allow Planck emission to space, extratropical cyclones are driven by that contrast between warm and cold sectors of the cyclone, and Planck damping acts to diminish that contrast. But I think we both decided that that's enough of extratropical cyclones.
Ryan, what's Planck radiative damping?
It's sigma t to the 4th, so Stefan Boltzmann, like as you warmer things emit more energy than colder things, basically. Yeah, so that seems to be the first order thing that's going on there, and but I think we're both looking forward to looking at something besides extratropical cyclone energy budgets, and so next I think we're going to start looking at how to improve regional climate change. We'll probably be equally as useless on that topic, but I'm sure Eric will do very well with that. And Aiden is kind of broadly looking at how tropical cyclones respond to a warming climate. And one of the interesting things that's going on is, this is a map actually from Sisson's paper, but on the left you see the observed pattern of surface temperature change over, I think this last 40 years or something like that. And on the right is what a couple of models predict should have happened over the last 40 years. And obviously they look very different. And Aidan is kind of looking into what are the implications of this difference in the pattern of warming in terms of projections of tropical cyclone frequency. You may say, you know, why is that really relevant to the future? And I think the answer to that is we're not really convinced that the observed pattern of trend on the left is just internal variability. I mean, we used to think that maybe 5 or 6 years ago, but now I think there's growing opinion and evidence in the modeling community that a sustained trend of that magnitude, of that duration, is really kind of outside the range of internal variability as models predicted. So maybe this is actually the pattern of temperature change that we will see in the future, and models are fundamentally wrong in some aspect of that pattern of warming. And so that could have broader implications for things like precipitation change and tropical cyclone change. Next up, we have Chen Young, and Chen Young is looking at aerosol cloud interactions. And that's of interest because in terms of the anthropogenic forcings of climate, the largest uncertainty we have is in terms of how aerosols modify cloud albedo. That's essentially what aerosol cloud interaction is. As you add more aerosols to the atmosphere, it makes clouds brighter. We don't really have good constraints on that within models. And so I think he's working very rapidly. He's already, I think we just talked yesterday, I think he's already ready to start writing his first paper, but and that will focus on kind of plots I'm showing here, which is really sort of the first observational validation at a global scale of aerosol cloud interactions in climate models. And the way climate models tend to manifest this aerosol cloud interactions is models with a higher climate sensitivity would normally project more warming over the historical period, but that's offset because those models also tend to have a higher aerosol cloud interaction, which is a cooling effect. And so those two things tend to offset each other in climate models. And low sensitivity climate models tend to have a weaker ACI. So there's a very strong correlation in terms of the IPCC climate models, their correlation of climate sensitivity versus aerosol cloud interaction. High sensitivity models have a high aerosol cloud interaction to offset it, and low sensitivity models have a weak one. And this is a figure where he's taken observations and compared them to the model projections. It doesn't really show up very well, but I think you can kind of get the picture that it appears that the high sensitivity models are more consistent in terms of their simulation of the observed aerosol cloud interaction than low sensitivity models. So that's kind of the bottom line there. And then lastly, the work that Priam is going to be looking at is kind of an extension of work that Ryan did when he was here, which is when we're measuring radiative forcing, we never really measure the actual energy balance. We measure things like the changes in CO2 concentration or the changes in methane, but we never actually monitor or directly measure how those changes alter the energy balance at the top of the atmosphere. And Ryan wrote a paper showing that we could actually measure this from space using satellite measurements. And Priam is going to continue working on that. Ryan actually just got he's at GFDL now, he just got a big 5-year, $3 million grant from NASA to do this. So Priam's going to be helping us work on that project. And just a note to my former students, when you go out there and start getting big research grants, don't forget your advisor on those things. Okay. So now on to kind of the subject of this talk, which is looking at radiative feedbacks in the context of the development of tropical cyclones. And this is work that Xunan Wu and Bosong Zhang did when they were students here, and it kind of, Xunan is continuing on some of this work now. They're both postdocs. Xunan's at Oklahoma and Bo is at Princeton. So Brian gave a talk on convective aggregation just 2 weeks ago or something like that. So we all know convective aggregation, a deep dive into entropy and information theory and all sorts of things that I'm still trying to understand. So, just briefly, convective aggregation refers to the tendency for convection to self-organize into coherent spatial clusters. And this is an example from a model simulation here. And you can see the white areas of convection. And this model is a very idealized model. It's completely uniform. The boundary conditions, the surface temperature, everything is completely uniform. So there's nothing that preferentially should favor convection in one part of the model domain versus the other. So on the left, you kind of see that with convection randomly dispersed. And on the right, at some point, the model just spontaneously decides to move all that aggregation together into one location. So that's a very interesting phenomenon. And there's a pretty rich literature on this. It goes back, Brian can probably correct me if I'm wrong, but I think Isaac had one of the first modeling studies of this phenomenon. And it triggered a lot of interest and a lot of research on this topic from the modeling perspective. And we've known from those modeling studies that radiative feedbacks play an important role in helping to trigger that self-aggregation. There's other processes also involved, but certainly radiation has been shown to be one important process that helps lead to that aggregation of convection. How does this relate to tropical cyclones? Well, if you take one of these very idealized model simulations and you move it, far enough away from the equator that it has some Coriolis force to it, that organized convection can also further organize into tropical cyclones. So in that context, we can actually think of tropical cyclones as one form of convective self-organization. Maybe a very special form, but nevertheless, we can view it through that lens. But unlike, I would say, convective aggregation, radiation has been kind of extensively studied for a couple of decades now. The role of radiation in facilitating the organization of tropical cyclones has maybe been less frequently studied, and I think that's understandable because in part, if you think of the diabatic heating, latent heating is probably 2 orders of magnitude larger in a fully developed tropical cyclone than radiative heating tendencies. So naturally, I think the focus, if you're looking at tropical cyclone development, would be on the larger term, latent heating. And in fact, that's where Xunan first started looking at. So Xunan was looking at satellite measurements of ice water content, and these come from a satellite called CloudSat, which is like a profiling radar on a satellite that can retrieve cloud, liquid, and ice water content. And what he did is he looked, there's like a decade or more of these measurements, and composited all the overpasses of tropical cyclones. And then he took those overpasses and looked at tropical cyclones that intensified within 24 hours after the satellite passed over it, and tropical cyclones which weakened within 24 hours after the satellite passed over. And this shows the composites of ice water content for tropical cyclones that strengthen versus tropical cyclones that weaken, and the bottom is the difference. So you see tropical cyclones that are about to undergo strengthening tend to have more ice water content than tropical cyclones that are about to undergo weakening. And you could further decompose these composites into different categories. So instead of looking at all tropical cyclones, you can do them by category. And now he's kind of folded the overpass. But it seems obvious, but this is kind of the center of the eye where 0 is. On these composites, he's averaged the radial distance. So the center of the eye here is now on the left, and then you're getting further out into the rain bands as you go to the right. And so even when you further separate that into different intensity categories, you see the same pattern that storms that are about to undergo strengthening have more ice water than storms that are about to undergo weakening, with the exception of major hurricanes. And so, our first interpretation of this naturally was that this is a ice water content is just a proxy for latent heat release. That storms are about to undergo intensification are having more latent heat release than storms that are about to undergo weakening. The only problem with that interpretation is that if you look at surface rainfall, which is kind of a column integrated measure of latent heat release, the signal isn't quite as clear. So these are the same cross sections for the same composites, but this shows precipitation, and red shows storms that are about to undergo strengthening, and blue shows storms that are about to undergo weakening. And there is some signature there for tropical depressions and maybe minor hurricanes. Tropical storms is a little dicey, and just overall that it doesn't look as clear. Like you're getting larger precipitation, outside the eye than inside the eye. So it's a little bit less clear. Let's just put it that way. So that got us thinking maybe there's something else going on. And the other thing that clouds do besides release latent heat is they absorb infrared radiation, right? So maybe what we're seeing in the cloud water content is the effect of clouds on absorbing infrared radiation. And so we can look at that from the same set of satellite measurements by computing basically something called the atmospheric cloud radiative effect, and that measures the convergence of radiative heat in the column of the atmosphere due to the presence of clouds. So you're just looking at how much heat clouds are able to converge into that atmospheric column. And this is all basically exclusively in the long wave. Like the solar part of this is very small. So we're really looking at how clouds are trapping long wave heat within the atmospheric column. And if you do that, a much clearer picture kind of emerges in the composites, where you see strengthening storms are converging much more heat into the atmospheric column than weakening storms. And that's true for basically all categories except for the major TC category. These composites were kind of limited in terms of their spatial extent. They only go to about 500 kilometers on either side of the eye. So we wanted to look at a slightly bigger picture of that. So he went back and actually went to a different satellite called Ceres, which actually measures radiative fluxes. So it's measuring the outgoing long-wave radiation, and it's also able to retrieve that radiative flux information at the surface. And then he redid those composites, so now we get a bigger picture, but also kind of a full two-dimensional picture of how this convergence of radiative heat in the atmosphere, what it looks like and how it compares between weakening and intensifying storms. So the left column shows weakening storms, the middle column shows intensifying storms, and then the right is the difference. So red is heating the column and blue is cooling the column. And then it's separated into different categories. And again, you see kind of this going picture where storms that are about to undergo intensification tend to have more radiative heating near the storm center than storms that are about to undergo weakening. All right. But this is, there could be other things causing this. It could just be that storms are, as they're about to undergo intensification, or also have stronger updrafts and they're generating more cloud cover. So this, this doesn't necessarily indicate that there's a causal relationship here between the radiative heating and the intensity change. So to really look at causal relationships, you kind of need models, so you can do sensitivity experiments. So what Shinan did with Dave Nolan's help is to take the Whorf model and then do two sets of simulations, kind of very similar to what the early studies on convective aggregation did, which was in the control run, you allow radiation to be fully interactive, but in the perturbation run, you spatially homogenize the radiative heating within the model domain. So each level in the atmospheric model, there's no gradient in radiative heating. It's all the same, right? And when you do that, these are simulations. The control simulations, you develop a tropical cyclone, but if you homogenize the radiative heating within the model domain, it struggles and oftentimes simply doesn't generate a tropical cyclone at all, right? So this is more convincing evidence that there's a causal relationship here between the TC genesis and these spatial contrasts in radiative heating. And so he did a number of simulations with this, and again, you see that basic picture emerge, where if you homogenize radiative heating within the model domain, you really suppress the likelihood of TC development. And there's been a number of studies in the past 5 or 6 years that have kind of really emphasized the role. Alison Wang at FSU has done a lot of this work in her group. And I think there's much broader acceptance within this portion of the tropical cyclone community that radiative heating does provide an important mechanism for TC genesis. And how does it generate? How does it radiation facilitating the genesis? Is a picture from the paper by Rupert et al., which is, again from Alison Wang's group. It shows, if you have a tropical disturbance of some part that's generating some cloud cover, at the early stages of development, the latent heat release here may be pretty small, right, as it's struggling to develop, but you still have enough ascent that you can generate cloud cover, and that cloud cover, once you get any significant high clouds of any thickness at all, they become very efficient absorbers very quickly, so that really helps to trap and heat the column underneath them. And that contrast in heating, where you're heating the center, cooling the atmosphere outside of it, that generates a secondary circulation that's helping to further transport moist static energy into the center of the storm and facilitating its development. So that all seems, pretty clear. So that's the basic picture. It's pretty straightforward. And Shinan did this with a variety of initial conditions, did a lot of experiments with this. And again, one of the things that these highlighted is that, and here's 3 sets of graphs where black is the control and green is the homogenized radiation. Going left to right, you're starting with weaker vortices on the left and stronger vortices on the right. And the point here simply is that radiation plays a more important role in jump-starting the weaker vortices than it does the stronger vortices, which again kind of makes sense. If you're starting with a very weak vortex, you're going to have much less latent heating, and radiative heating, relatively speaking, is going to be more important than if you start with a stronger vortex. So with that kind of as the background, we wanted to ask a few more questions about this. One is that almost all the model simulations that I've shown, like all of that Shinan did here, are with very idealized conditions. Everything is completely homogenized, uniform surface temperatures, uniform shear, no large-scale gradients of any kind within the model domain. And that's obviously not very realistic. So we wanted to ask, does radiation still play an important role in the development of TCs when you have a more realistic set of boundary conditions? And then the other question, is this just some kind of esoteric thing that we like to study in models, or is it actually relevant at all for operational TC prediction? And then lastly, and this is some work that Shinan is working on now, which may seem kind of counterintuitive, is can you actually have dry air facilitate TC development? Can dry air, we tend to think of dry air as inhibiting TC development, but I'll have to show that there is potentially a role for dry air to accelerate TC development. So the first part, is this relevant under realistic conditions? We went out and found a model that has realistic boundary conditions and does a pretty good job of simulating TCs. This is high-RAM, GFDL high-RAM model. It's 25 kilometer resolution. And we took this model and forced it with observed SSTs over this period, and you can see it does a relatively good job of reproducing the observed climatology of TC tracks, both spatially and year-to-year variability. And then what Bo did is to kind of redo the set of experiments that Shunan did to suppress the coupling between radiation and dynamics in this global model and see what happened to TC counts when you suppress that feedback between radiation, between clouds, radiation, and dynamics. Basically, we're disabling that coupling. And when he did that, so these are TC counts, the control. ClimeRad refers to the experiment where we suppressed the radiative coupling between dynamics and radiation. And there's about a 20% reduction. So again, it's consistent. It shows that this is a significant process, even under realistic boundary conditions. So yes, the answer to that first question is yes. The next thing we want to do is was this process at all relevant for operational prediction? So to look at that, we collaborated with Gus across the street and looked at H-Wharf B forecast for the 2018 season. So H-Wharf B is a very good, now it's been decommissioned with, I forget what the new name of the model is, but it's essentially an operational forecast model. And this is work that Shunan did, and he looked at like 500 different forecast cycles in the 2018 season, and he compared this radiative flux convergence in the model simulations from the same storm with observations on a kind of a storm-by-storm basis. And so this is the comparison. The top shows the satellite observations of the radiative flux convergence from clouds in the atmospheric column. And the bottom shows the H-Wharf simulations. And then that's what's shown on the leftmost column. And then the three right columns show the anomalies that are associated with storms intensifying at different rates. So these are kind of slowly intensifying storms to rapidly intensifying storms on the right. And in general, the model captures that contrast in rate of heating between weakly and more rapidly intensifying storms. But we really wanted to ask is, does this feedback influence the quality of the forecast? And so to look at that, what Shunan did, and I have to think about this to make sure I get it right. So he looked at, again, he composited strengthening storms from weakening storms. But then he further composited strengthening storms into strengthening storms that were accurately predicted by the model and strengthening storms that were incorrect. So you have correct strengthening forecasts and incorrect strengthening forecasts. And you also have correct weakening forecasts and incorrect weakening forecasts. And then he differenced the radiative heating between correct strengthening minus correct weakening and incorrect strengthening minus incorrect weakening. Okay. And that's what's shown here. So on the left are observations. All the observations are correct, right? So that's strengthening minus weakening storms in the observations. And then for the correct intensity forecast, that's shown in the middle column, and they generally show the same pattern as the observations. But then you go to the incorrect forecast and you see that the pattern looks very different. In fact, for the weaker storms, it's almost reversed, where you have more rate of cooling. You have rate of cooling in the center and rate of heating outside the storm, rather than the opposite. So, so my interpretation of this is not that the feedbacks are by itself responsible for the incorrect forecast, but rather that this feedback is making correct forecasts better and incorrect forecasts worse, right? So it's a feedback. It's amplifying the intensity change in either direction. And if you're getting it right, it's going to make that forecast better. If you're getting it wrong, it's going to make that forecast worse. I don't think we've definitively shown that yet. We need another set of sensitivity experiments to do that, and maybe we can try to do something like that in the future. But that's my take home from this set of comparisons. Okay, so the answer to that is, yeah, it seems that this feedback is important for accurately getting intensity predictions, even in an operational context. And so the last one is, can dry air actually accelerate TC development? So the thinking here is that it's not the heating by itself that's driving the intensification, but it's rather the spatial contrast between you have heating near the storm center and cooling in the environment. And so if you can enhance that contrast, you'll generate that secondary circulation that will transport more energy into the storm center. And so you can enhance that contrast two ways. You can either add clouds in the center and create more radiative heating in the storm center, or you could increase the radiative cooling in the environment. And since the environment is already largely cloud-free, really the only other way to increase the radiative cooling in the environment is to dry it, right? So if you can make the environment drier, that will increase the radiative cooling, and then maybe that will also lead to facilitate the TC development. And this is again just to highlight that intensifying TCs both have stronger heating in the center, but also stronger cooling in the environment. You see that in the observations as well, right? So what Shunan did was, in the radiation code, he redid the same set of simulations with WRF, but then in the radiation code, he took a domain average water vapor profile and fed that into the radiation to create a second set of simulations in which only in the radiation there is no spatial contrast in moisture. So as far as the radiation knows, the moisture is completely uniform horizontally within domain, whereas in the control there's obviously variations in moisture. So he did a set of simulations here. This is with an initial vortex strength of 7 meters per second, which is pretty weak, but you can see, and then these, actually, one more thing. And then in the radiation, he put in differing values of relative humidity at each layer. So the control has fully interactive moisture with the radiation. And then these different colored lines represent different values of relative humidity that were imposed in the radiation code throughout the domain. And so this shows, with this vortex strength, if you make the relative humidity in the free troposphere very dry, like between 5 and 20%, you do see slightly faster development than if it has a more humid free troposphere, right? But it's not much, right? You really have to look and, okay, just during this period here, do you really see any difference? But then if you take that vortex and you make it weaker, so these are simulations here with 6 meters per second, 5 meters per second, 4, and 3, then you see that there's much greater separation between storms that, storms with a drier free troposphere tend to accelerate much faster, or accelerate, and if you have a moist free troposphere, they simply don't develop at all. So for this very early stage of development, and these are pretty weak vortices, so this might almost be considered pre-genesis, before you even reach like a tropical depression stage, when you're trying to get to some level of disturbance, that dry environmental air can be important in facilitating the eventual genesis of a disturbance. And just to show that there is actually some observational evidence to support this, these are satellite composites of mid-tropospheric relative humidity, again between strengthening and weakening storms. And you see, as you would expect, that strengthening storms tend to have more moisture near the storm center, but there's also a tendency for those strengthening storms to have a drier environment around them. Well, the take-home point for that is, yeah, I think for very weak vortices, it could be important. There can be a role for dry air to actually facilitate the development, or maybe the pregenesis of these weak vortices. And then this kind of gets into, where we're maybe taking this research in the future, and maybe some of the things that Aiden will be working on. That are these radiative feedbacks at all relevant to understanding how TCs will change in a warming climate? And this goes back, one of the first studies, I think the first modeling study, to try to look at how tropical cyclones would change in a warming climate, was by Tony Broccoli and Suki Manabe back in 1990. And they used like a 5-degree, maybe it was 7.5 degree resolution GCM to simulate tropical cyclones and look at how they change in a warming climate. And that greatly endeared them to the tropical cyclone community when they presented that work at the AMS tropical meeting. I think Tony still has nightmares and flashbacks about that, about that meeting. But one of the things that's interesting there is they did 2 sets of simulations, one with fixed clouds. This is back when climate models often used prescribed cloud cover. So they had one simulation with fixed clouds and one simulation with variable clouds. And the fixed cloud experiments had fewer storms and shorter-lived storms than the variable clouds. It's the same basic result that Bo found when he did these simulations with a 1/4 degree model that simulates very realistic TC climatology. So maybe they were justified in some of their conclusions here. The other thing is that interactive radiation also has a larger reduction in tropical cyclones in these experiments than if you do fixed radiation. And that's also the same thing that Bo found when he did CO2 experiments with a high resolution model. And so one of the questions we have is that in fact related to, again, going back to the clear sky cooling in the environment, if you add CO2, you're going to be reducing that contrast in radiative heating between the environment and the storm center. And so maybe that's one important mechanism that leads to a sort of a global reduction in TCs in a warmer climate. And yeah, so that's kind of, I think, the picture here. So when you warm the climate, you're increasing CO2, but you're also increasing water vapor in the environment. So you might think that that would reduce the spatial contrast in radiative heating, and maybe that's an important mechanism for tropical cyclone change. And I think that's kind of the general area that hopefully Aiden will be looking into here is, we kind of the consensus on TCs and climate change is that there'll be fewer but stronger. And at least for me, it's not exactly clear what the processes are that lead to that. Why are there fewer TCs? Why are there fewer Cat 1s and 2s, but more 4s and 5s in a warmer climate? Why don't Cat 1s and 2s increase in a warmer climate? I don't think we've kind of accepted that, but I don't think there's a simple mechanism that's been put forth that can kind of explain that. So I'd like to maybe dig into that a little deeper using maybe some of the WRF simulations to better understand these mechanisms. So anyways, that's all I had for my presentation. Thank you for listening to this, and happy to take any questions if there are.
So in that schematic that you just showed, you talked about radiative heating from the cyclones, and that must mostly be from the cirrus sample. So it would be a direct way to look at like weak and strong radiative heating events be to just look at the size of the animal, the cirrus sample. It seems like people are doing that with convective aggregation, but I haven't seen you mention that in this context.
Yeah, that's, I think you're right. If there was a systematic change in TC size, You know, with climate, then you might expect changes, like if there, you know, was maybe a shrinkage of annual cloud amount in TCs as the climate warmed, which some people have argued for in other contexts, not within TCs, but yeah, that could be an important role. Yeah, I mean, it's certainly something that I think could play a role in that sort of process. You're right.
Did you look at that with like intensifying and weakening?
No,
TCs
you know,
in earlier analysis?
we didn't look at that at all. Yeah, it might be something worth looking at.
Oh, you mentioned 2 orders of magnitude smaller than latent heating. That's wildly too small. If you sort of bulk regress ACRE against L times rainfall, you know, how much, I used to try to call this the latent heat of radiation. You know, how many photons is a kilogram of vapor going to capture on its way to raining out? And you do that on a kind of daily scale, 5-degree scale. It's about 15%. My walking around number, 15% of the latent heating is implicit.
Okay, so it's only
heating.
1 order of magnitude. Maybe.
Yeah, and not even that. Good solid 15%.
Okay.
But it's a little bit geometry dependent. And the way is you get more bang for your buck of a unit of cloud if you put it on in an otherwise clear sky than you do by thickening the IWC of an already thick, opaque anvil, right? So I might think in these in the center of these cyclones, the latent heat of radiation is less than 15%. Doesn't mean it's not important, but it'd be nice to know that number to sort of map that. On whatever scale it makes sense to talk about the water creates, you know, cloud and rain, and you track the cloud all the way through its life cycle and capture all the radiation it's going to capture. If there's some way to do that for this, I wonder if that's kind of this 15% I walk around with, or more like only 10, but still important, of course.
Yeah. And along that line, the other thing, you know, Dave has this, I forget exactly what it's called, it's like the efficiency of diabatic heating in TC intensification. And so not all diabatic heating is the same, so it's really diabatic heating near the eye wall.
Yeah, heating where it's hot. You do a temperature variance budget, sort of. Heating where it's hot matters more. So you get, it's already cloudy, so you're not getting as much, but it's heating where it's heating in a juicy spot.
Yeah.
So anyway, there's a whole kind of way to like quantify, I feel like, this the energetics of this ACRE, and it's not just that it's tiny and then surprisingly large. It's 15% is a good first guess. I wonder if in these models you could just multiply the latent heat of condensation by 1.15, see how far that gets you. For instance, as a comparison or something.
Yeah, so if you redid the homogenized radiation but just put a 1.15 in there, would you get back to the control?
Yeah, exactly.
Yeah.
That would be like a baseline,
A baseline number.
Yeah.
And and I wonder about that because when I think of Dave, and I think Dave's listening, so maybe you can chime in on this, but exactly how that fits into the picture, because when if I understand Dave's generation maps correctly, they don't really have a role for the environment in amplifying the contrast in heating. Is it really just heating in high MSE regions, or if you cool in low MSE regions and then generate that secondary circulation, is that part of that diagnosis?
Yeah.
So. Britton?
So really interesting talk. The kind of TC genesis world, there have been these studies showing precipitation area is more important in determining genesis rather than precipitation intensity. And so, would you say that kind of relates to sort of radiational feedback? So, for example, if you have, if it is the cirrus top contributing to those long wave feedbacks, that if you care less about the intensity rainfall but the coverage, that kind of allows for those longer feedback.
So you're arguing that the aerial coverage of precipitation may also kind of be a proxy for the radiative impact rather than the actual latent heating component?
But I was curious if that fits into what you've seen.
Yeah, I mean, we didn't look at that diagnostic, but I could see that also being similar. I mean, that was one of the things that, try to get back to that. Yeah, like that. So this was, when we looked at ice water content, you saw this increase in ice water content kind of throughout at least this 1,000-kilometer cross section of the storm. It wasn't just within the eye wall area, which is where you get the greatest bang for your buck in terms of generating intensity from latent heat release. So, yeah, I think like this would be consistent with that kind of aerial expansion, and maybe kind of relevant to what Akita was talking about in terms of cirrus canopy size.
I also think of like an initial disturbance, very loosely organized area of convection. If you even just fill in the holes of like convection through region, then maybe you have a more consistent tabletop that can feed into these feedbacks. It's kind of what I was thinking.
Yeah.
But it seems to plan like there's been like this your work and others showing long wave feedbacks being the early stage, and it seems to fit in with the observational evidence from different proxies. So it makes it, I guess, more believable to me.
Mm-hmm.
There is a comment from Dave Nolan in the chat.
I don't see it here because it's in presenter mode. And you want me to?
Maybe you can see it on the main screen where your mouse cursor is.
I see the secondary circulation. Okay, so Dave says, I see the secondary circulation of radiative forcing is helping to precondition the inner core for more and stronger thunderstorms in the center and not driving the intensification itself. Okay. Yeah, I guess, and maybe we're thinking about the same thing there, but to me, I look at it as an upgradient transport of moist static energy. So you're transporting more moist static energy into the storm center, and that seems to be the diagnostic of the day for understanding like convective aggregation and other things. The moist static energy variance budget that Allison Wing developed in her work with Carrie in her PhD. But I think we're saying the same thing there. What, Dave? You can unmute if you want, Dave.
We're saying the same thing.
Okay. Good to know. I feel. I don't know how to get out of this.
Sharon, all the way in the back.
Yeah, just a more of a comment and a data point to corroborate the results of your 2023 paper with Shutnan on the relationship between environmental humidity and the probability of genesis. So a former student, Will Kamarami, looked at that in the ECMWF ensemble, and it's sort of buried somewhere in a paper, I think from 2014. And he found that there was, just sort of for a full season, 2010, that there was a fairly distinct negative correlation between the central vorticity building in an incipient disturbance and the environmental relative humidity. So yeah, I think that just, even though it just uses sort of model ensembles, it sort of backs up.
Okay. Yeah, it'd be great. I'll have to look at that. And Shinan is working on this paper now, so you can include that as you write. It's good to have more evidence to support it.
Cool. Yeah, I hope I've got the result right.
All right, well, thank you all for coming. Thank you, Brian.
Thank you.